Hello folks, we are back here and now we are going to talk about Gauss's law, or how to calculate the electric field of symmetrical charge distributions. Think of Gauss's law, an easy way of calculating the electric field, not just of point charges, but a continuous distribution of charges in a rather easy way. Okay, Gauss's law is not a new law of physics. Gauss's law is just a different format of Coulomb's law. Okay, so let's write that down here. Gauss's law is not a new law of physics. Instead, it is just a different format of Coulomb's law. And you need to understand that. Okay, and what are we going to do? What are we going to do? What are we going to do this chapter? Okay, we will determine the electric field of different charge distributions using Gauss's law. Charge distributions, okay, by the way, those is not any type of charge distribution, but a specific type of charge distribution that we call, that has distributions that has symmetry using Gauss's law. You don't even have to know Coulomb's law. But you have to know the following. One, the mathematical format of Gauss's law. Two, that positive charges are source of electric fields and negative charges are sinks of the electric field. That's what you have to know. So suppose that you do not know Coulomb's law and you want to calculate the electric field using Gauss's law instead. Okay? So let me give you the format of Gauss's law. Mathematical, and that's what you have to memorize. Let's go back here. I'm going to show you in your book. Okay, you can skip this part. It's just more like a qualitative introduction for Gauss's law. Okay, so here you go. But okay, before we introduce Gauss's law, I have to tell you about something that we call the electric flux. Okay, so we have some illustrations here of the electric flux, and we use the electric flux in the Gauss's law. Before we go about introducing Gauss's law, first you have to understand, to know. You have to know, not to understand, have to know and understand, right? What is the electric flux? Flux is a quantity that is defined not just for the electric field, but also for the magnetic field, and even the gravitational field, by the way. Okay? Flux is a concept that's generic enough. And used for the magnetic and gravitational fields. What is the electric flux? What the electric flux is? So let's take a look here at this drawing. Okay, suppose that I'm going to give you the simplest illustration of electric flux. Here you go. Suppose that you have the simplest example of electric flux. Oh, even better, I'm going to use what I already have here. Here you go. I'm going to use this illustration here. Oh, even better, let's see. Let's see if I can get it. Yeah, this one. I'm going to copy that and paste somewhere else. Remember this drawing? So I'm going to use that. Here you go. Oh yeah, right here, I already have it. Oh yeah, here you go, I have this one, I don't need to copy it. Okay, suppose that you have an electric field in space. A uniform electric field. I want to make it a uniform to make the simplest example that you can have out there. I'm going to label that the electric. Oh yeah, I already have electric field here. Okay. The electric flux of an electric field is determined with respect to an imaginary surface. The surface can be opened or the surface can be closed. Okay? So here you go. Let's go back here. The electric flux, here you go, can be calculated with respect to a given surface. This surface can be open or closed. A given surface, here you go. And I'm going to say a given imaginary surface of area A. The surface has to be imaginary. It's not a solid surface of area A. The surface can be open or the surface can be closed. Here in my drawing, I have a open surface. It's not closed. It's like just a flat surface. Just like this one that you see here in your drawing. The difference is that the electric field in this case makes an angle with the surface. Okay? We don't have another illustration. So if I were to draw the surface sideways to make it simple, here you go. That's how it look like. You know, sideways. So you don't see the actual plate, right? In this specific case, again, I'm doing the simplest case that you can think of. The area vector of the surface is always perpendicular to the tangent of the surface. Okay, so we have the surface has an area, but the surface also has an area vector. Okay, let's go here. The surface of area A, the area, here you go, the area, here you go, the area of the surface, the area A of the surface can be represented by a vector that is perpendicular to the tangent of the surface. For a flat planar surface, this area vector is perpendicular to the surface itself. Okay, so more specific, in a more generic sense, okay, in a more generic sense, in a more correct sense, the area vector is perpendicular to the tangent of the surface. You have the surface, you get the tangent to the surface, and that area vector must be perpendicular to that tangent. For a flat surface, you know, you don't need to say that it's must be tangent, perpendicular to the tangent of the surface, okay? Because the surface is flat. And we just say that it's perpendicular to the surface itself. Here you go. Special case, a simple special case. Surface, area vector, perpendicular. Then we're going to do different types of surface, and you're going to understand what I mean. Okay? Note see that the electric field, I'm going to put my electric field right in here. Note see my electric field is parallel to the area vector. Okay? So you have the most electric field lines crossing this surface because there's no angle in there. Think about that. Think about the surface. Suppose it wasn't like that, but suppose that surface was like that, had an angle, okay? You wouldn't get all the electric field lines crossing the surface. Make sense? So here you go. I'm gonna do a drawing here, a nice drawing. I'm gonna put it the surface red and thick so you can visualize it better. Don't forget this is an imaginary surface. Because it's an imaginary surface, I'm going to put it dashed. Okay? Imaginary surface. And now, right now you have most of the lines crossing the surface because the area vector is parallel to the electric field line. However, if the area vector weren't parallel and the surface were a little bit rotated, here you go, had a rotation, let's see, rotation right in here. Here you go, I'm rotating the surface, the imaginary surface. And I'm going to displace it a little bit more. Now you're going to have less electric field lines crossing the surface. Not only, here goes, not only this surface would be rotated, but the area vector would be rotated as well. Okay, 31 degrees. Here you go. Let's go at it. 31 degrees. See that? So how do we, so in this case here, we have less numbers of electric field lines crossing the surface. Here we have the most, because the area vector is oriented parallel to the electric field. Okay, here we have less, and we can go even to the extreme in which you have no electric field whatsoever crossing the area, the imaginary area. Let me show you how we do that. We do that by positioning this surface in this orientation here. See that? No electric field lines crossing the surface whatsoever. And I gotta also reorient my area vector. Okay? Let's go to 90 degrees. Here you go, 90 degrees. Here you go, you got it. Area vector. In this specific case, the number of lines, electric field lines, or electric field vectors that cross the imaginary area is zero. It's exactly zero. Zero, you know, something in between, and maximum. We can do, can do zero and here you go. Let's do it this way. Maximum and minimum. Minimum means zero, and anywhere in between. So how do we define the vector, the flux, electric flux after this illustration? Okay, so this, like I said, is just a qualitative way so you can understand where the flux is coming from. Well, the way we define the electric flux is defined by the following equation. Go insert my equation right in here. The flux are usually represented by the capital letter phi right in here. Greek letter phi right in here. We put a subscript E to remind you that is the electric flux. We can also have a magnetic flux and other types of flux. We write down the magnitude of the electric flux, the area, and the cosine of the angle between those two vectors. Right? That's how it is defined, theta. Right? If theta is equal to 0 degrees, then flux is maximum. You know, if theta oh, what did I do here? Okay. If theta is equal to 90 degrees, then flux is 0 or minimum. If theta is in between 0 and 90 degrees, if theta is between 0 and 90 degrees, then the flux is going to be between, you know. So that's the definition of flux. Then flux is between, is maximum or EA. If the theta is between 0 and 90 degrees, then the flux is anywhere here. I'm going to put that. The flux is what? Anywhere between 0 and EA. Make sense? That's what you have to know about the electric flux. Remember, that's not Gauss's law. Gauss's law uses this idea of electric flux. And those are illustrations of the book. Okay, don't forget that theta is the angle between the area vector. That's always perpendicular to the surface, or normal to the first surface. We also refer that as a normal to the surface. Normal is a more generic concept than perpendicular. Is the angle between the area vector and the electric field. Okay? So we have here the same equation. So what about Gauss's law? How does it take the form? Okay, Gauss's law takes the following form. Here you go. It's written here. Right in here. Gauss's law relies on calculating the flux, electric flux, across a closed imaginary surface. It's gotta be closed, not open like the other one. Imaginary surface. That encloses an electric charge. Okay, I'm going to give you an example so you understand. With this technique, we can calculate the electric field of a given charge distribution. So how does it look like? Okay, so here you go. I'm gonna how do we write down Gauss's law. I'm going to write down like that. I'm going to put this is the electric flux of a closed surface enclosing an electric charge. Okay, so let's go back here. You're going to see the formula. 4 pi kq, or q divided by epsilon naught. That's what you have to know. Okay, and by the way, q, and we usually write down as being q enclosed by the surface. The book didn't do that, but we usually do that, okay? Most books do that. Just to remind you. Oh, not here. This one here. Divide by epsilon naught. Epsilon naught. Okay? That's how we do it. Let's do an example. So only doing examples you're going to understand how to use Gauss's law. Examples. We start with the simple example. Point charge. The simplest of all examples. Okay. Find the electric field of a point charge using find the electric field of a point charge using Gauss's law. Here I gotta put that. We'll instead just do the way the book did, right? 4 pi k, right? 4 pi kq enclosed. Here you go, like that. ENC. Here you go. Point charge of charge q, right? Using Gauss's law. Simplest of all examples. Solution. Remember that in order to solve this type of problem, you can do only 4 electric charge distributions that have a symmetry. Okay? So I'm going to show you how to solve that. Let's see here. Okay, here you go. We have a point charge. We already know that we have electric fields that emanate from this positive electric charge. Remember that? You already know that. So if we are going to see here, if we are going to, okay, let's start with this one here. That's what you want here. Here. If you want to find out the electric field anywhere here around this charge, okay? You do know, let me get this thing out of the way here first. You do know that positive electric charges, the electric field emanates from positive electric charges, okay? So you're going to use this piece of information. And then what you're going to do, you're going to find a Gaussian, imaginary Gaussian surface that you can use to find out the exact equation for the electric field. Okay? So, let's start with the most generic possible Gaussian surface. Something like that. Okay? In this situation, this specific situation, what do you have? We have that the area vector may keep on making different angles with respect to the electric field. Do you see that? Right? So what does it mean? It means that I didn't choose the proper Gaussian surface. It would be very difficult to calculate the electric field for this type of Gaussian surface, which, by the way, is not symmetric. So what do? We come up with a better Gaussian surface. We come up with a Gaussian surface that's centered with respect to the electric charge. Do you see that here? We know that the electric fields emanate from the electric charge, and instead of getting a surface, a Gaussian surface that's off-center, instead we use this simple type of surface that's exactly centered at the surface. If you look into that into details, you are going to see. Remember that I told you that the area vector is going to be perpendicular to the tangent to the circle. Here's the to the circle, to the surface, to the sphere. Okay, this is a sphere that I'm representing as a circle. The tangent to the sphere is this line here that I'm drawing, and the area vector is perpendicular to the tangent. So what happens? By choosing a proper Gaussian surface, we get an area vector that is parallel to the electric field, whether it's here, whether it is here, here, or anywhere else. Okay? The electric fields are emanating from the point charge. Is a point charge in space, a single point charge in space. And the area vector, let's see, oh, here you go, the area vector is right in here. See that? Perpendicular, not perpendicular, normal to that spherical surface, to that imaginary spherical surface. Now we can start calculating my electric field of this point charge. You already know the result, right? But we're going to do it again using Gauss's law. And by the way, you know, this sphere that you see right in here has a radius r. Let's do that again. Here you go. Play the movie. We start with the point charge, magnitude q. Okay. We get the x and y axis. We want to calculate the electric field of this charge. What do we do next? We first, visualize the electric field lines that are coming out of this charge. The electric field lines are emanating from the positive point charge. Then we look for a Gaussian surface that is symmetrical with respect to this charge distribution. The only one that you're going to find is the surface, is a spherical surface centered at the charge. The next thing that you do, you recognize that the area vectors are oriented parallel to the electric field, because you choose the proper anywhere along the surface, by the way. That's what I mean by getting a symmetric surface. And that helps solve our problem. And then what's the next? Okay, this surface, by the way, has a radius r, a generic radius r. And now we can start solving our problem. I don't need that anymore. Can you? Okay. Go back to the equation for Gauss's law. Right in here. I'm going to use 4 pi k cubed. 4 pi k cubed. Okay. Q enclosed, right? Q enclosed is equal to big Q. And now we have to calculate the flux through that spherical surface. And what do we do? The flux through that spherical surface is the electric field times the area times cosine of theta. In that specific case, theta is equal to 0 degrees, so I don't have to worry about the cosine of theta. Oh, and by the way, the electric field here in this case is the electric field. I should have put that here, emphasize that. Is the electric field on the Gaussian surface, okay? On the surface. I'm going to put the electric field on the surface, throughout the surface. So here you go, going back here. I'm talking about the electric field at this surface, at this point here on the surface. The electric field at this point here on the surface. The electric field at this point here on the surface, and so on. Okay? It's not the electric field at this point and the electric field at this point. No. It's the electric field at the very point, at the very place of the surface. So we can emphasize that by put that S subscript to remind you that is the electric field at the surface of the Gaussian surface, at the Gaussian surface. on the Gaussian surface, right? So that's how the flux go. Here you go. And then what do we do next? We calculate the area of my sphere. I already stated that area has a radius r, a genetic radius r, and the area of a sphere is going to be what? 4 pi r squared that you get from mass, right? Geometry, here you go. And now we have this equation here to determine the electric field of my point charge. 4 pi cancels out with 4 pi. And we get exactly, what is that? Coulomb's law. Get my r squared here on the other side. Okay, kq r squared. If the charge is negative, the fields point towards the charge. That's the magnitude. And by the way, is the electric field anywhere at any distance genetic distance r from the charge? That's one example. Let's do another one. I do all those, a bunch of examples like that for my students so they can understand how to calculate the electric field, okay? Here you go. What's the next one? Let me see. I'm not gonna do this one. This one is difficult. This one we cannot do with this at this course level, okay? But I'm gonna do this one here. It's a spherical shell now. The other one is more difficult, requires calculus, so I'm gonna skip that one. Here is not a spherical shell. Here is a solid sphere with charge distributions throughout it. For this one, I can only do for the field outside the sphere, okay? Inside the sphere, it requires calculus. Inside the sphere requires calculus, but outside is just end up being that of a point charge. It's exactly the same procedure. Here you go. But inside the sphere, we cannot do it because it requires calculus. Here you go. Find the electric field of a spherical uniform spherical charge distribution, of a uniform spherical charge distribution outside. Here you go. Outside a uniform spherical charge distribution of net charge Q. Here too should be net charge big Q, right? Only outside to calculate. Only outside to calculate inside. You need calculus. Okay. Solution. You know, the procedure is the same. As that of a point charge. And you get exactly the same equation. Okay, here you go. So a spherical distribution of electric charges the electric field outside it behaves just like of that of point charge. Example 1, example 2. What are we going to do next? Now we're going to do a spherical shell. Find the electric field outside and inside a spherical, uniformly distributed, uniform distribution of charges in a thin spherical shell. net charge big Q. Okay, both inside and outside. Find the electric field outside and inside. Yeah, this one we can do. This one we can do because it doesn't require any calculus. I'm going to illustrate that for you. Here's the sphere, solid sphere with a uniform distribution of charges throughout its volume, right? And here's my spherical shell. There's nothing there inside the sphere. Charge big Q, so let's say we have positive charges there, uniformly distributed in this shell, but no charges inside. The radius of the spherical shell is big R. I gotta write that down too, okay? Find the electric field outside and inside a uniform distribution of charges in a thin spherical shell of radius R and net charge big Q. Okay, so we're going to do outside first. Outside is just like that of a point charge distribution, right? X-axis, y-axis. Okay, big R is the radius of the spherical shell. Oh, we start with the center of the spherical shell. Here you go. Here's my Gaussian surface, a spherical Gaussian surface. Imaginary. Start with the inside. Charge. But the result is different inside the spherical shell. Okay, so let's go ahead. Here you go. I'm going to copy that, right? The flux throughout a closed surface is going to be equal to 4 pi k Q enclosed. But now my Gaussian surface does not enclose any electric charges whatsoever. So the net charge in this case is going to be 0. Okay? The Q enclosed is going to be 0. So we can write that down, 0 here. Not only you can write that down, but let's assume, that there is an electric field inside here being emanating from the inner shell towards the center, right? Let's assume. And let's assume that this also has spherical symmetry. Okay? This electric field, no, I'm going to put that here. This flux, right, would be E times A. The area of the shell of the Gaussian surface is finite. We do know that the area of the surface is finite. Don't forget the area of the imaginary surface is going to be 4 pi R squared. Go. But this equation here must be equal to 0. R is not 0. 4 is not 0. Pi is not 0. So what does it mean? It means that E must be 0. Okay? R has a finite number. There you go. I put R, let's see. Oh, I didn't illustrate the R, lowercase. Oh yeah, I illustrate here. Lowercase I, R. So I can solve that for 0 divided by 4 pi squared, which by the way is 0. So inside the sphere, the electric field is inside the spherical shield. Spherical shell. Inside the spherical shell, for R less than big R, the electric field is 0. Outside the spherical shell is exactly the same result of a point charge. Okay, so you do the same thing, you get the imaginary Gaussian surface. the electric field, the vector area, and you get the electric field of a point charge. Outside the spherical shell, R greater than R, the electric field is that of a point charge as well. So here we go. Let's see how the book is doing here. You go through a sphere. Okay, he's doing with numerical examples here. Okay, what's the flux for a sphere of radius 5 that has a point charge at its center? He's asking what's going to be the flux. You can do that numerically there at home. I'm doing it in the most generic fashion. Electric field at distance from a long thin wire. We're going to do it for a long thin wire now. That's what we have it in my next point. Here you go. Long thin wire that's charged. Okay? Charged. For this type of problem, you know, you have to define what we call a linear charge distribution, lambda. Okay? That's what I'm doing, and you're gonna see why. There's a reason for that. So I'm gonna define to you what lambda is, but let's say we have a discharge Q, very long wire, by the way. Okay? If you look along the axis of the wire, you look at something like that. And let's say that the charge is positive, right? What am I doing here? I'm doing my Gaussian surface uniform distribution, but my Gaussian surface, you know, is going to be a cylinder. Okay, a cylinder. Sideways, we're going to see an electric field that emanates from this line that moves, you know, radially, sideways. But if you look on the other plane with the z-axis pointing towards you, that cylindrical surface is this one right here, right? That's a cylindrical surface that looks like a rectangle. And how does it look like? The cylindrical surface has a radius r, and those are the electric field emanating from the point charge, from the linear charge distribution. Okay, so what comes next? Here you go. I'm going to get what we have right in here is the area vector on the cylindrical surface. Don't forget that the cylindrical surface must be a closed surface, right? Let me see if I can. Here you go. I'm gonna make it appear that it is a cylindrical surface for you. Here you go. I'm gonna put no fill. Okay, like that. Do you believe now? And I'm gonna make it dashed as well. Like that. And now instead of no fill, I'm gonna put a fill there. Here you go. Do you believe me? Now we have a, and this guy is supposed, it's gonna be difficult to do that. Yeah, I'll have to make it transparent. There's no fill, okay? And you would have the same surface here on the other side. Oh, don't do that. Right in here. Okay. Here's the area vector at the cylindrical surface, but we also have area vectors at the covers, right? area vector here. The electric field here in this region is parallel to this area, but the electric field with respect to this area here is perpendicular. Those are the area vectors of the caps. Area vectors of the caps. So now we're going to have three surfaces. The cylindrical surface, this cap here on the right side, and this other cap here on the left side. So let's start working on that. Right? And I didn't got all the surface. Let's say this length here is L. Did I put L there? No, I didn't put L. It's a good idea to write it down L, right? Let's put that L, length L for this surface. Equal for this imaginary surface. I like this other arrow right in here. Oh, you didn't do it. Okay, did it on the left side. We do on the right side as well. And I'm gonna put this guy here on the bottom so it doesn't get in the way. And I'm gonna call this length L. I'm gonna make it big L with the color black. Move it up. Okay. So let's go ahead. Example 3, uniform distribution term. Since cylinder. Okay, now we gotta do for the very large linear distribution. Example 4. Find the electric field outside electric field to a linear distribution, uniform distribution, linear distribution of charges of a very long charge uniformly distributed okay, of linear charge density lambda, linear charge density lambda. Symbol. Ooh, nope. Symbol. Here you go. Here you go. Lambda. What lambda is? You know, lambda is delta Q over delta X. Okay, delta X. By the way, uniform, which is constant, by the way. That's what lambda is, okay? Now it's clear, right? Symbol. And symbol as well. Solution. You already saw the procedure. The procedure for this problem, we use a cylindrical shell for the Gaussian surface of radius r. Just like you saw. Oh. and by the way, and length L. So we have three surfaces. So we have three surfaces. The side cylindrical surface and the two planar caps at the end of the cylinder. Okay, let's see it again. I'm gonna get the other. Here you go. The cylindrical surface right in here. That's one surface, and then those two caps here at the end. Those are three surfaces. Let's repeat. Here you go. Electric flux of the closed surface. Here you go. We get that. That's Gauss's law. Okay. 4 pi k Q enclosed. Okay, what's going to be my Q enclosed? My Q enclosed here in this case is going to be given, just look back. Just look back at my lambda right in here. See that? I know lambda. And the Q enclosed is going to be lambda times the length of the cylinder. Make sense? Okay? Q enclosed, let's write it down here below, is going to be equal to lambda times the length of my cylindrical surface, where this guy here is known. This one is not known yet, but you're going to see that doesn't make any difference whether you know it or not. I got the most generic one. Substituting that here, we got, okay, something like that. I did everything that I could have done on the right side. Now I have to work out this guy right in here. Okay, so here we go. What's going to be the electric field? Let's call each of those surfaces surface 1, 2, and 3. Okay? It's going to be, so our flux is going to be electric. Oh, by the way, if you go back here to this cylinder, okay? Because we have this line is very long, we should expect that the electric field here at this surface is going to be exactly the same. Okay, so let's write that down. The electric field at the surface of the Gaussian, the electric field at the Gaussian surface, here you go, at the Gaussian surface, on the Gaussian surface, is going to be the same because the linear charge distribution is very long. Okay? But only, I can say that only for that point on the surface. Okay? I cannot tell you anything about the electric field right in here at this other surface with a smaller radius. I cannot tell you anything about the electric field here outside. Most likely it's going to be smaller than this one here because it's further away from the source. So here you go. Let's continue here. Electric field is going to be surface 1. By the way, cosine of theta. Cosine of theta 1. Cosine of theta 1. Okay, that's the cylindrical surface. Then we have those other two surfaces, the two caps. Electric field A2 cosine theta 2. Electric field A3 cosine theta 3. That's how we do step by step. Close, don't forget the closed surface equal to this guy right in here. Okay, I'm going to label all those surfaces. Here you go. This one is going to be surface A1. Even better, I'm going to put surface 1. Right? Like that. The other one on the right side is going to be surface 2. Cap 2, right? And the other one on the left side is going to be my surface 3. Cap 3. Like that. Like that. Okay. You saw in the previous, oh yeah, here you go. See this area here, here is area number 2, here's area number 3. Let's put that. That's going to be area 1. Subscript. That's going to be my area 2. It's going to be my area 3. Like that. The electric field here is parallel to this guy, right? So we have that cosine of theta 1 is going to be 1. The electric field at cap 2 is going to be perpendicular to the area vector. So my cosine of theta 2 is going to be 0. And similarly, the area vector here is perpendicular to the electric field as well. So we're going to get another 0 here. And we are left only with this term. Here we go. And we don't need this one here on the left side anymore, right? That's going to be 0 and 0. What else? Oh, now we gotta calculate the area 1. Area 1 is going to be what? It's going to be the area of the cylindrical surface. 2 pi r 2 pi r L. Do you remember? We created that L out of nothing, and yet we don't have to worry about it because it's going to cancel out. We don't need that A1 anymore. And look what we find. We find that for a linear charge distribution, 2 pi cancels out. We're left with 2 only. And pass the R to the other side, and we find that the electric field decreases with the inverse of the distance. Oh, like that. Okay, so next, one more. Let's see. How much time we're doing? 1 hour, right? Uniformly charged cylinder. We're not going to do the uniformly charged cylinder because just like the uniformly charged sphere requires requires calculus to calculate the charge at the center. But for uniformly charged cylindrical shell, it's similar. Okay? So let's see here. Here we go. I'm gonna give you the answer for the for the other ones. Example 5. Find the electric field due to a uniformly charged cylinder of radius r. Okay, outside the cylinder. Just like before, in the case only outside, calculate inside, you need calculus, just like the other situation. Field of a very long uniformly charged cylinder of radius r. Outside electric field outside, here you go. Outside a very long uniformly charged cylinder of radius r with and then radius r. What else you have to know? With volumetric charge density. I need to show you I need to tell you that sigma we usually represent like that. You need that sigma, where delta x, delta k over delta v. Oh, that's v. Yeah, which is constant. I need to show you that. Okay. Outside only outside. Since in calculate inside, you need calculus. Just like we did before, you need a cylindrical shell for the Gaussian surface. Gaussian surface of radius r and length L. As before, we have 3 different surfaces: the cylindrical surface and the 2 planar caps, the 2 planar surfaces at the end of the cylinder. So here you go. Let's go right in here, just outside. We're doing that just outside. Okay? Right in here. But now consider that this guy has a radius r. We get this surface. Okay? We go step by step just like we found before. Here you go. We already know that the electric field is going. Oh, let's see here. First, let's do the Q enclosed, right? The Q enclosed is going to be different. It's slightly different because now we have a 3-dimensional surface. Here you go. Let's find the Q enclosed first. Q enclosed in this case is going to be what? Is going to be my sigma No, not sigma, sorry, it's rho. It's not sigma, we usually call that rho. You go, oh, rho. Yeah, sorry. Okay, here's gonna be rho. We call rho for volumetric density. I don't like this rho. Hey, it's this one that I want, not the other one. Here you go, times the volume. The enclosed volume, by the way. Let's put that here. Enclosed volume. The enclosed volume is what? Let's take a look here. This guy has radius big R, right? Enclosed volume of the cylinder is pi r squared times L. That's what the volume of the cylinder is all about. Pi, let's see, yeah, radius R, okay. Pi R square times L. That's the volume. Area times length. Okay, so here go. 4 pi k. We put it right in here. See, it's slightly different, but you're gonna get the same result that you got before. And then we're going to the electric field on the Gaussian surface is exactly the same thing as before, okay? So here you go. The electric field on this Gaussian surface is going to be the same because the cylindrical charge distribution is very long, but only on that surface of same radius. Cylindrical charge distribution is very long. There are three surfaces. There are fluxes through three surfaces, right? Through surface 2 and 3 is going to be 0. We are left only with the area of surface 1. But the flux on the right side is going to be different. That's what needs to be fixed. Okay, here you go, fixed. It's going to be fixed. Is that okay? Oh, there's something wrong here. Pi r square. Oh yeah, okay, we do have pi square. Let's put a pi square here. Doing on the fly, right? In real time. That's what we should put in there. Hopefully I didn't make a mistake, right? 4 pi, yes, that's right. It's supposed to be pi square, no problem. Pi square, just simplify. We are left with this one. Okay, and the area of the Gaussian surface is going to be just like you saw before. Oh, let's copy and paste this one here. L is going to cancel out with L, right? Let me just copy and paste this one. 2 pi is going to cancel with one of the, with this 4 and one of the pi's. The L is going to cancel out as well. Oh. And we pass the R to the other side. We get 2 pi k. Wait a minute, there's something wrong that I'm missing here. I'm missing, oh yeah, see that? I'm missing the volumetric charge density here. That's the volume, that's the volumetric charge density, right? 4 pi k, okay. Here you go. Very important. I missed that one before. Here you go. That is a row. We call that a row. Keep track of those things. That's why I like to use that other software. They keep track of all of that for you. Sometimes we make a mistake with those software. And let's see. Okay, I cancel everything that I could have canceled out. And now I cancel the L, I cancel the 2, I cancel the pi. And now all I have to do is to divide by little r. The little r is the generic distance from the center of the cylinder. I like to write that down like that. Okay, let's compare. Lambda over r, rho over r. But we choose 2 pi, 2 pi k r squared. Okay. And then we're going to do another one. Let's see. 1 hour and 15 minutes doing that. You know what? Do the example 5 on your own. Try to do that on your own. And I'm going to formulate that for you. And we're going to do a different one. Find the electric field outside and inside. A very good practice. A cylindrical shell uniformly charged with surface charge density. Here you go. Now we're going to use this, sigma. That's what it is. Divided by the A equal to constant. The surface charge density uniform. Find the electric field outside and inside a very long cylindrical shell. Very long, uniformly charged cylindrical shell with surface charge density. Surface charge density of radius r. Okay, of radius r. And surface charge density outside and inside. Outside and inside. I'm gonna do just inside because this one inside is similar to what we saw for the spherical shell. Here you go. That's the solid cylinder, right? What about this one? This one is a cylindrical shell. You have charges only here on the outside. The electric field on the inside is 0. And go ahead and calculate the electric field on the outside. On the inside, the E field equal to 0. 0. Calculate the field on the outside. And the last one. Let's do the last one. Otherwise, we're going to stay here too long. Okay, the last one. No numerical, just the generic, right? We did that. See that? They explained that to you. Imaginary cylindrical surface. I did all of that. Oh, he didn't do for the planar distribution. Interesting. I'll do that for you. You already know the result because I already told you. Here you go. I'm going to do that here for the plate. This one right in here. Okay? How do I know that the electric field is uniform? Well, I'm going to calculate the electric field for this distribution. But before I start doing that, let's do qualitatively. Let's find qualitatively how the electric field would look like for this distribution. Okay? See, this is the electric field due to this charge here at the very edge of my plate. And here is the electric field due to this other charge right in here. Okay? If this point is very close to the surface, the electric field will be almost in the horizontal direction. If this point is right in the middle of the plate, the field is going to be exactly on the horizontal direction. Now, if this plate is very long, infinitely long, then the electric field will always be horizontal. There won't be any y component of the electric field. Okay, so that's how I know that the electric field lines are going to be horizontal, just by doing the simple qualitative treatment. Okay, so how do we find exactly the electric field? Again, we use an imaginary cylindrical surface, Gaussian surface. This Gaussian surface is better, right? We already know that the electric field goes in this direction. We already know that. We have an area vector A. That's the surface 3, right? The cylindrical surface. Let's put A instead of the A. And that's an important difference between the cylindrical distribution of charges and this one. In the cylindrical distribution of charges, this area vector was parallel to the electric field. Now, the area vector that's parallel to the electric field is the area vector on the caps. Okay? Cap 1, cap 2, surface 3 now. So, let's formulate the problem. Okay, we're going to do example 6 now. Find the electric field. Find the electric field due to a very large charged planar surface. Can be square, can be circular, okay? Of surface charge density sigma. There is no radius here in this case. Doesn't have to be, it's going to be only outside in this case. Okay? So I already did part of the problem. Here you go. I know what is the density here. Sigma, right? Because it's very large, we have so much charge, That's why we treat it as being a surface charge density. That's why. So let's go ahead and repeat everything. First, we find what's the charge enclosed, the charge that is enclosed. Okay? The charge enclosed by that cylinder. The charge enclosed by that cylinder is going to be sigma area. Okay? Sigma area. Would be a circular area that projects over the surface of this guy. Okay, that's what the right side of this equation is all about. Now we have to find out the flux, right? Here you go. It's going to be kind of similar to that. It's going to be area, electric field area 1, electric field area 2, electric field area 3. And the right side of this equation is going to be something like that. We know that, but we still do not know that, we do not know that. The area we know. This area that you see here, let's see what's A1, A2, and A3. What I label, okay, that's A1. A1 is A, okay? A1 is going to be A, the same as A. Oh. A3 also, right? That's A3. No, A2. A3 is the other one. A2 is going to be A as well. A3 is going to be, 2 pi r, that's the radius of this guy, times, let's say L. Okay, let's put that like that. 2 pi r times L. But then you are going to see that we don't even have to worry about that. 2 pi r times L. The radius of that circle that you saw. The angle theta 3 is 90 degrees. Right? The angle theta 3 is 90 degrees. Consequently, that term disappeared. Unlike the other one, right? Unlike the other one, it doesn't disappear. The angle theta 1 and theta 2 is 0 degrees. Take a look at the drawing. Area vector and electric field. So this guy disappears. Becomes 1. Because I choose the same area, we can sum up those two terms. Okay? And look, the surprise, our surprise. The electric field, let's continue. I didn't finish, right? Here you go. I'm going to cancel out the 2. I'm going to cancel out the A. The 4 canceled out. The A is canceled out as well. And look what we get. We get an electric field that does not depend on the distance from the plate. Remember that I told you it was a uniform field? Yeah, there is no dependence on this distance from the plate. That's kind of surprising, right? That's what we call the uniform electric field. And that's what we saw previously here, but I didn't tell you how I got to that result. Let me show you. When I was doing the electric charge in a uniform electric field, remember that? Here you go. Okay? See? It's a uniform electric field. Now I prove to you it's a uniform electric field. If it's positive, it's away. If it's negative, it's into the plate. However, if you put one negative plate next to a positive plate, the fields inside are going to sum up to each other, and the fields outside are going to cancel out. Okay? Here you go. Like that. So that's what we have. The book didn't do the plate, but now you know how it's done for the infinitely large planar surface that's charged. So we're going to finish here, and we are done with chapter 16 in the book. Okay? Right in here, Gauss's law. That's Gauss's law. Gauss's law for electric fields. Next time we're going to do the electric potential, which was already somewhat covered in the lab. But now you're going to learn that for good. So thank you very much, and I see you again.